This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning. So, in the first part of the lecture today, I just want to finish off what we were discussing yesterday because it got a bit rushed at the end. And then we'll look at problem set 2. Okay? So, we left off yesterday thinking about how to draw so-called Bode plots, which are just plots of the frequency response in terms of the magnitude of the transfer function evaluated at s equals j omega on one plot on a log scale, and the phase of the transfer function evaluated at s equals j omega on a linear log plot. Okay, and we saw that given a general transfer function that is real rational, okay, in the sense that it's a ratio of two polynomials, which we can always factor in the way shown by the fundamental theorem of algebra, okay. And if we take the magnitude of that and then the log, all right, we see that we can express that in terms of a sum of simple terms, okay. And similarly, the phase just decomposes because the phase naturally decomposes anyway. The phase of the product is just the sum of the phases. Okay, so we were spending time looking at, well, what do objects like this look like when evaluated at s equals j omega? Okay, and what do things like this look like? So we were looking at diagrams like this. Okay, these little vectors here show how this function, I don't know why this is blocked there. This function varies as we evaluate it at s equal to points along the j omega axis, the imaginary axis. Okay, so this little vector is what you get when you evaluate this at s equals j.1 on t. Okay, so what we're showing here are little vectors that correspond to 1 on t times ts plus 1 evaluated at s equals j omega for different values of omega. All right, whereas we were up here looking at functions that have this form, which is just ts plus 1, where in this case t is equal to 0.1. The point of looking at these terms is that at low frequency they always have a gain of 1, because when I evaluate this at s equals j0, I'm just left with 1. Right? So that's why we normalise. But to draw these vectors, you can't normalise first. Okay? Effectively what we're doing is moving the origin to what makes this function evaluate to 0. Okay, so to figure out what something like this would look like, we would have to look at these little vectors and multiply by t. Okay, which will change the magnitude but won't have any impact on the phase. All right, so you can see here that for small omega, small frequencies, okay, we get a magnitude of this vector will be 1 on t times t is 1. Okay, and that's what we're getting here. Right, and this is just a complex number. Right, those t's cancel, you're left with j.1 plus 1, so the magnitude of that will be the square root of 0.1 squared plus 1 squared, which is the square root of 1.01, which is approximately equal to 1. And as we continue to increase omega up here, the length of that vector only ranges from size 1 up to something of size root 2, which is 1 point something, right? So it's not much bigger than 1, all the way up to j times omega equal to 1 on t. Okay. If we now look at a frequency that's 10 times bigger than that, okay, you can see that the length of that vector now starts varying like omega, right? The length of this is almost just like taking the length there, all right? And so you're getting something that will continue to grow as omega grows as we move up the imaginary axis like this. And you can see that the phase starts off at 0, okay, and then starts increasing as we increase omega, okay. At this frequency here, the phase will be pi on 4 radians, okay, because we have a triangle where that length is the same as that length, okay. We'll give you pi on 4, 45 degrees, if you like, and the angle here is nearly at pi on 2, okay. So once we go about a decade above this frequency, so 10 times that frequency, the angle is almost pi on 2. All right, so you can see that the phase is varying from 0 and increases up to pi on 2. And it does so over a range of frequencies from about a decade below, so 0.1 of that frequency that corresponds to the value of S that makes this equal to 0, okay, which just makes that equal to that, up to about a decade above. All right, so you can see that in these plots that the variation in the phase as it increases, okay, is from about a decade below where it's 45 degrees and a decade above. Okay. So, you know, we saw that looking at these terms, which appear here, is just can be, you know, determined by looking at this, right? Because, we have these properties of the log, right? So the magnitude of 1 on A is 1 on the magnitude of A, right? And the log of 1 on the magnitude of A is just minus the log, right? So that just flips the plot around. It mirrors it in the 0 dB line, okay? And so instead of going up, it goes down, all right? And the phase of 1 on A is related to the phase of A in this way. It's just multiplication by -1. And so you see that, you know, this just flips again in the 0 radians axis. All right? So where these kick up is determined by where these things are equal to 0. All right, where was I? Where was the other picture? Now you can do the same thing when there's a complex conjugate pair of poles, okay? You draw the vectors in exactly the same way, all right? So let's say we've got a function that looks like this, like this, okay? So that's going to have a conjugate pair of zeros, right? So at these complex values of S, this will evaluate to 0, okay? I want to see how the magnitude and phase of this changes when we evaluate this at S equals j omega and increase omega from 0 up to plus infinity. So we can do exactly the same thing as we did over here, right? Draw these little vectors. I don't know why this thing doesn't work. Can you see the pointer on the screen? Yeah, okay. You draw these little vectors again to the value of omega that you're looking at, all right? So at omega equals 0, we've got these two little vectors, all right? And if you work out what the size of these things is and put it into dB, this is the value you get, right? So it depends on the so-called natural frequency of this conjugate pair of zeros, okay? And you can see that the phase will be 0, right? Because the phase of this one is minus this, okay? And the phase of this one is plus this, and they're of the same size. So when you add them together, they give you 0, right? So the phase starts at 0, and we start increasing, okay, omega. The phase will become positive because this angle is getting bigger and this angle is going towards 0. And so the phase will start being positive, okay? And it will continue to increase and eventually be pi on 2 plus pi on 2. It'll go to pi. All right? So as we increase omega from 0 up to infinity, the phase of this changes from 0 up to pi. Right? We're getting pi on 2 from each of those, just like we got pi on 2 from one of these as omega approaches infinity. Okay? Now if we look at the magnitudes of these things and how they change as we increase frequency, remember that what we're doing is we're looking at the magnitude of each of these. They appear in a product here. But when we take the log, okay, then we take the sum of the log of the size of this one and the log of the size of this one. Okay, and you can see what's happening here is that this one is getting smaller for some time and then it gets bigger again, whereas this one is always getting bigger. The fact that this one gets smaller, and it might be a value that's less than 1, so when we take the log of it, it's negative value and it pulls the plot down like this. Okay, before it starts rising up again, and when it rises up, it's like we've got the sum of this thing, which is varying like omega, and the sum of this this thing, which also varies like omega, right? So it goes up at 40 dB per decade. All right, so that's why, yeah, and these are looking at 0. So if you're looking at 1 on this, it would be something that pops up like that. Okay, which is consistent with these sorts of pictures here. All right, so you can understand the second order case where the poles or the zeros appear in a complex conjugate pair in exactly the same way. We're just looking at these little vectors and how they change in magnitude and phase as we change the point at which we're evaluating the function along the imaginary axis. So I'd encourage you to play around with pictures like this to get an understanding of why these Bode plots have the shape that they do. All right. So we left off last time thinking about this plotting the Bode plot, so the gain and phase plot of this transfer function. I realise that this is probably a bit hard to see, so let me do another example, right? Starting from scratch. Okay, so we know that we can, once we've factored our transfer function like this by pulling out the 10 here so that this appears in a form such that the component of the Bode plot that corresponds to this will start at 0 dB, right? The component of the Bode plot corresponding to this will start at 0 dB. Okay, we're just normalising so that this has gain 1, each component here has gain 1 at 0 frequency. Now, of course, you can't ever see 0 frequency on a log scale because the log of 0 is minus infinity, so you've got to go to minus infinity to see 0. So you never quite see 0 frequency on a Bode plot, okay, but this is on a log scale, so a decade down below this it'll be 0.01, and then a decade below that, so 1 unit on this scale further down would be then 0.01, 0.001 and so forth, so it gets small quickly. All right. Now we know we can draw the Bode plot by just looking at how each of these simpler functions behave across frequency. Okay, so let's start with this one here. Can you see that or not? Is that too hard to see? Yes? No? I don't know. Can you see it? Just? Maybe I'll change the pen. Can you see that? Whoops, hang on. Can you see that better? Is that better? No? Let me just do it with this. So let's consider this term here. Okay? So really what we're interested in looking at is 1 on j omega, and we're looking at the magnitude of that. Okay, so that'll be 1 on omega. All right? If we take the log of that and multiply it by 20, right, we get minus 20 log omega. All right? Now, at omega equals 1, we get log of 1, which is 0, right? So let's just mark that point there, right? This is the 0 dB line, all right? And we can see that as a function of log omega, this is just like a straight line with slope of minus 20. And that must pass through this point, right? So it'll start here and it'll end here if we just look at the decade above and below where it crosses the 0 dB line, and it'll just be like this, okay? And it'll keep going down at 20 dB per decade. So at 100, I haven't drawn a very straight line, it should be at minus 40 dB. Okay, so that's just this component here. Now let's look at this component here. Okay, we're just going to take 20 log 1 on 10, okay, which is minus 20 log 10. Okay, so it'll be a line down here somewhere, right? Okay. Everyone's happy with that. So that's that next component. Will just be this line across here. Of course, that doesn't change with frequency. It's the same value at all frequencies. Now, if we look at this component here, all right, we're going to, at low frequencies, it's going to have a gain of just 1, right, which on the dB scale is 0, right? And we saw that it keeps that magnitude roughly all the way up to omega equals 1, all right? And after that, it'll kick up, and it'll kick up at 20 dB per decade. Okay? So at 10, it'll hit 20 dB. Now let's look at this term. Okay? So again, at low frequencies, it just has a gain of 1, which on the dB scale is 0. And it'll stay roughly there until we hit 10. Okay? Because if we evaluate that at j omega 10, right, then the magnitude we're getting is equal to root 2. So it won't actually be sitting at 0 dB, it'll be at 3 dB. Okay, but as a straight line approximation, we keep it at 0 there, and then it will kick down at 20 dB per decade. So by the time it gets to 100, which is 10 times 10, it'll hit minus 20 dB, and then it will keep going. Okay, so that's what each of the components looks like, all right? And so we just have to add them together, all right? And we're adding together on this dB scale. Okay, so that's 20, that's 0, that's minus 20, that's minus 40, right? Without, you know, looking at the magnitude, this is like multiplying by 10. This is like multiplying by 1. This is like multiplying by 0.1. This is like multiplying by 0.01. Okay? So we just have to add them together, right? Because that's the advantage of working with things on the log scale. We just have to add all of these things together, all right? So, of course, this guy keeps on going up forever at a slope of minus 20, right? Okay, so at low frequencies, I'm adding this, these two, and this, but on the dB scale, right? So these contribute 0, right? And this will bring this point down to 0 because 20 plus minus 20 is 0. And so we'll just have a straight line parallel to the blue one, okay, going down at 20 dB per decade, right? So by the time we get here, it should be a straight line to about here, okay? Now, beyond the frequency omega equals 1 radian per second, okay, we've got this guy going up and this guy going down. We're adding those together. When these 2 points add together, they add together to give you 0, right? Plus the 0 corresponding to the purple line, plus the minus 20 corresponding to the red line. So it flattens off, okay, and goes along at minus 20 dB, okay, until we get to this frequency here. So these guys still cancel each other out, okay, but now we've got this guy contributing a negative amount to the sum, all right, and this guy is still contributing minus 20, and so it kicks down again at 20 dB per decade. So the overall magnitude plot is what I've drawn in black, and the point is that I've arrived at that by looking at each component of this factored form of the transfer function and just had to add them together. Now these are just straight line approximations, all right? So, you know, when I was drawing this one here, sorry, I should have put minus 3 dB because it's 1 on this guy, all right? So the actual component due to this guy here, it's not sitting at 0 dB all the way, it's very close, and then it starts to break away and it'll hit minus 3 dB and then go like that. Okay, but this is a pretty good straight line approximation of that curve. Okay, so the black one will probably look more like this, and then at the corners it'll be not quite at the corner, then it'll flatten off, and then it'll be not quite at the corner and flatten off. But the straight line approximation is pretty good. Okay, we can now draw the phase. Okay, so again we've got each component, right? Let's look at what the phase of this is. Well, the phase of this is just the phase of 1 on j omega, right? So for all omega, that's just a point on the imaginary axis. So it'll be minus the phase of j omega, which is just minus pi on 2 radians, right? The phase is the same for all frequencies. So on this plot, we get, that term contributes to a phase like this, okay? The phase of this is just the phase of a real number that's positive, and the phase of any positive real number is just 0. So what did I draw? I drew that in red before. Okay, so that'll just be this line, okay, where phase is 0. Then we've got this guy, all right, and the phase of terms like this, they start off at 0, which is what we saw, right? At 1, it'll be 45 degrees, and at 10, it'll be nearly pi on 2, and beyond that, it'll be very close to pi on 2. So that term looks kind of like this, and you get the phase varying between 0 and pi on 2 over 2 decades, okay? And at the frequency that corresponds to making this term 0, it's 45, okay? And so then we're left with this guy here. That's 1 on a factor that looks like that, so the phase will flip, it'll decrease as omega increases. At the value of s that makes this equal to 0, that's 10, we'll have minus 45, okay? It'll start off at 0, right? From about a decade below the value of s that makes that equal to 0, it will start decreasing towards minus 45, okay? And a decade above, it'll be almost at minus pi on 2, but then beyond that, it'll be pretty much at minus pi on 2. Okay, so now we just have to add all of those things together, right? So at the start, all of these ones are at 0, okay, so they don't contribute, and we just start off at minus pi on 2, okay? And you can see that here, the green one starts to kick up, right? So the phase will start to kick up from minus pi on 2, all right? But then beyond 1, the purple one here is kicking down, all right? And so they will start to cancel each other out a bit more, and then eventually we end up back at minus pi on 2, right? Because over here the green and the purple cancel out, and we're just with the blue, and the red contributes nothing. Okay, so that's how you can, by hand, get a feeling for what the Bode plots look like. Okay, this is just a picture of what MATLAB spits out, and you can see it has exactly the same shape as the thing that I drew by hand. Right, so I'd encourage you to go through this example and any other examples that you might care to construct to confirm your understanding of how to draw Bode plots like this. Okay, it's very useful to, be able to just by hand know how the Bode plot is going to change when we add poles and zeros to transfer functions, because that's often what we do in control design. We start off with the model of the plant, and then we add poles and zeros to it by multiplying the plant transfer function by a controller transfer function before closing the loop. Okay, and so knowing how the product of the plant and controller transfer function will change as we add poles and zeros to it in terms of how the Bode plot changes is a useful thing, as we'll see later on. Okay, now quickly before looking at problem set 2, I just want to say something to help justify a statement that's made back here about the frequency response being something that's useful because we can think of signals more generally in terms of how their energy is distributed across frequency. Okay, so if we have a system with a transfer function g that's stable, okay, and if I put a step in and then turn it off after capital T seconds, okay, because this is stable, you would expect the output to respond with some transient, right? And if this stays on for long enough, it'll reach a steady state, right? The steady state value that we'll get to will be G0. Okay, we've seen that. And then when I turn it off again, we'll get another transient, and then eventually it will reach a steady value of 0. Okay. All right. So let's see what the transfer function evaluated at s equal to j omega can tell us about the behaviour here. You can see that what we're getting out of this stable transfer function is a distorted version of what went in. Okay, in steady state, it's exactly the same as what goes in, but when there are changes, okay, what comes out is a distorted version of the changes that go in. Okay, and the frequency response, so the transfer function evaluated at s equals j omega, tells you something about the distortion. Okay, this is just the Laplace transform of this. It just follows directly from the definition of the Laplace transform. We know that the Laplace transform of this output signal will just be the product of the transfer function and the Laplace transform of the input. Okay. Notice that because this signal is something that we can put inside an envelope corresponding to decaying exponentials, the j omega axis must be in the region of convergence for y. Okay, so we can legitimately evaluate the Laplace transform of y along the j omega axis. Okay, and if we just look at the magnitude of that now and ignore the phase, you can see that the magnitude of y evaluated at s equals j omega is equal to this expression here. Okay, so this is just algebra. All right, of course, this guy here is always just 1, right, because this is just something that's somewhere on the unit circle. Okay, and this guy here is a sinc function, and a sinc function looks like this. Okay, and of course what it looks like depends on t. It depends on how long we kept the input on for. Okay, the longer you keep it on, the bigger this gets, and the narrower this main lobe gets. Okay, so it turns into like an impulse. Okay, so the longer I leave it in, it starts looking like a little impulse in the frequency domain though. All right, and that's kind of suggesting that this signal has lots of energy at low frequency, right? And the longer I leave it on, the more energy it has at zero frequency. Okay, but if I turn it off at some time, you know, it still has substantial amounts of high frequency components. All right, so what's coming out, all right, is this times this. And so if your frequency response is something that does this, for example, okay, where that is, I don't know, some frequency, okay, it would correspond to something that looks like 1 on omega bar s plus 1, for example, would have a function like a frequency, a Bodie plot that looks like this, all right? And you can see, well, if omega bar is over here, all right, then almost all of this gets through undistorted, all right? But if omega bar is down here, then you get lots of distortion in the output signal relative to the signal that was put in, all right? If your transfer function were something that had a resonance, okay, then that would be amplifying components in the pulse input at these frequencies that line up with this. And you would expect in the time domain to have something that oscillates in the transient. All right? Because these components of the input get amplified by the transfer function at that frequency. Okay, so you can get a feeling for the transient part of the response of a system to step-like changes at the input, okay, by looking at the frequency response. Okay, by thinking of what's happening here as distortion that's arising due to this not just being flat at all frequencies. If this was just flat with a gain of 1 at all frequencies, everything you're putting in would come out and you'd get no distortion. Okay? Are there any questions on that? We're going to be spending a lot of time thinking about how signals have their energy distributed across frequency, right, when doing control design. Okay, so this is a useful way of thinking, and it's why we think a lot about the frequency response. Okay. All right, if there are no questions on that, let me just pull up problem set 2. Maybe that's the wrong one, I think. That's the wrong one. All right, so problem set 2 is looking at this system, which is something that we studied in problem set 1. Okay, so in problem set 1, we built a differential equation model for this system. Okay, it's just a DC motor that drives an inertial load that corresponds to an inverted pendulum. Okay, and we saw that you could get a transfer function that looks something like this. And the transfer function relates the Laplace transforms of the incremental signals associated with wiggling the input voltage across the terminals of the motor about some equilibrium value, okay, and the incremental signal corresponding to the position of the pendulum relative to an equilibrium value. Okay, so depending on the equilibrium, we get a different transfer function. Okay, so this is now saying, well, let's just look at a particular equilibrium. Okay, and that equilibrium will correspond to applying 0 across the terminals of the motor and the pendulum being in the upright position, so theta equal to 0. Okay, and in that case, this transfer function, assuming also that the inductance is negligible and the viscous damping due to the gearbox is negligible, okay, and that all of these parameters have been normalised and the moment of inertia has been set to this and the mass set to this, simplifies to this transfer function here. All right, so the first question is saying, well, is this incremental model stable or unstable? Well, if you rewrite this as s plus 3, s minus 3, you can see straight away that this system has a pole at s equals minus 3 and it has a pole at s equals 3. So there's one pole in the right half plane. And you only need one pole on the imaginary axis or the right half plane for the system to be such that the impulse response has a component that blows up as time goes to infinity. And that's what we say is unstable. And that should be consistent with your intuition that if I've got an inverted pendulum, right, if I tap it and don't do anything, it'll just fall down. Okay? So the theta continues to grow as time advances, corresponding to the thing flicking around. But of course, this is a linear model. The real model's non-linear, right? So the angle doesn't just continue to grow exponentially and blow up to infinity, right? That's what the linear model predicts. But the linear model is only valid for small angles, okay? And once the angle gets bigger than a certain amount, the linear model stops predicting it well. And to understand it properly, you need the full nonlinear model. So instead of just blowing up to infinity, eventually it just hangs down the bottom. All right? But that's because the linear model can't predict the behaviour all the way around. It can only predict the behaviour around the top. Okay? But nonetheless, this is, consistent with what you would think intuitively, that if you tap a pendulum, it won't return to its equilibrium value. It'll keep going. All right? So the next part is about saying, well, let's analyse a closed loop, all right? Control system for our model of the inverted pendulum. Okay, so the first part actually doesn't require you to, put anything in for GS, but later on we'll be putting this in for GS. So we've got a control system here, okay, that measures how far you've moved away from the equilibrium value of 0, right, compares it to a reference value, generates an error signal which goes into a controller that produces a signal which gets combined with a disturbance input, whatever's pushing on the top, okay, which then drives the dynamics of the inverted pendulum, okay? And what we want this closed loop to ensure is that this follows this, okay? And we want to make sure that it does so even when there's a disturbance acting on the system. All right? So this next question here is about saying, well, find closed loop transfer functions T and S, right, such that we can write down this expression for the relationship between these inputs of the closed loop system and this output. Right, so you've just got to write down a bunch of equations that you can read off the block diagram. Okay, so let's just try to write some of those down. All right, from the block diagram we can see that delta theta, right, I'm not going to write S because there's too many things to carry around, right, but this is a function of S, all right, will be G, right, times whatever this signal is. Okay, what's this signal? Well, it's di, right, plus this signal. What's this signal? This signal is C times this signal. What's this signal? It's R minus delta theta. Okay, that's what this represents. Okay, so there's one equation that we can write down. All right. So if we rearrange this equation to take this onto the same side as this, what do you get? You get delta theta. We're going to get plus GC delta theta, right? Because that G multiplies that C, which multiplies that delta theta. Okay, so taking that onto the other side gives you this, equal to G di plus G C R. Okay. Now, if I just take this out as a common factor, you get 1 plus GC delta theta equal to G di plus GCR. Okay, and if I divide both sides of that equation by this now, you get delta theta is equal to G on 1 plus GC di plus GC on 1 plus GCR. Okay, the advantage of working in the frequency domain is that everything becomes algebraic like this. All right, so this is what we call T. Okay, it's a transfer function that tells you how wiggling R makes delta theta wiggle. All right, and this, right, is what we call SI. It's a transfer function that tells us how wiggling the plant input disturbance causes delta theta to wiggle. All right? And we're getting that purely algebraically. And the key is to think of the block diagram simply as a graphical representation of a system of equations. Where did I get these equations from? I just read them off the block diagram. Right? Similarly, you can take a system of equations and turn them into a block diagram. They were one and the same. Right? This is just a graphical representation of some algebraic relationships. Okay? If you're not comfortable doing that, the only way to become comfortable with it is to practice doing it. Right? So I'm showing you how to do it. That's not enough. You've got to go away and practice it if you're not comfortable already with doing these sorts of things. All right. So the next questions are about saying, well, when the controller transfer function is given by the ratio of these two polynomials, okay, and the plant transfer function is given by this, okay, when are these closed loop transfer functions stable? Because the closed loop is only going to be able to make this follow this if the transfer function is stable, right? We've just seen an example of, I wiggle the input to a stable transfer function, it'll be able to follow it if it's got the right gain, okay? There might be some transients in between, but if it's an unstable transfer function, as soon as I wiggle this, there'll be components of the response that could blow up, and that's not what we want. Okay, so this question is saying, well, how do I choose these parameters in the controller to make sure both of these transfer functions are stable? Okay, the next one is then saying, well, when it's stable, what ensures, what's the behaviour of this signal here? And this signal here represents the tracking error, right? It's the difference between what you want delta theta to be and what delta theta is. okay? And that will depend on these controller parameters in some way. Right, the next bit is then saying, well, once you've got an expression for that, you can find conditions on those controller parameters to make sure that the error is always less than 1% in steady state. Right? And things like, I only want this much overshoot in the response and so forth. Okay, and the last bit is about the response of the system to a sinusoidal disturbance here. Okay, which will simply correspond to looking at this transfer function, okay, which here is just expressed in terms of some other transfer functions evaluated at s equals j omega, for omega equal to the frequency of the input sinusoid. Okay, so all of that sort of stuff follows algebraically, right, as shown in the reference solutions here. Okay, so we've just derived this relationship between these inputs to the closed loop system and this output of the closed loop system, if you like. We're interested in understanding how this signal behaves in response to wiggling these signals. These transfer functions tell you about those relationships. Okay? So really all that's happening here is we're substituting in the plant and controller transfer functions. Okay, so you can see that here. Is that big enough? So there's the controller transfer function. It's parameterized in terms of k and tau. Here's your plant transfer function. All right, so that's gc. On the bottom we've got 1 plus, that's cg, right? 1 plus cg, that's what's on the bottom there. Okay, and if you write that out, this is what you get. Right, it's a second order system. Okay, and of course what that second order system is depends on the controller parameters k and tau. If you change the controller parameters, you get a different closed loop transfer function. Right? Control system design is about choosing those parameters to get the right sort of behaviour. Most fundamentally, we want to make sure that this transfer function is stable. That's the first criterion that we have to satisfy. All right? Similarly, if you write down what S is, you get this transfer function and you see that they share poles. Okay? This polynomial is the same as this one. Okay? But this transfer function has an additional pole. That pole is at S equals -3, so it's a stable one. So to determine stability of this, we just need to check that the zeros of this polynomial both lie in the left half plane, which will also ensure stability of this transfer function. Right? We want both those transfer functions to be single, because we've got two inputs, two things that we can wiggle. Right? And for the closed loop to be unstable, it just takes one of those transfer functions to be unstable. And to get theta to exhibit unstable behaviour, you just need to wiggle the corresponding input in the right way. Okay? So this analysis here is just about looking at the zeros of this degree 2 polynomial. Okay? And we do that by reparameterizing this polynomial, as shown here, as the product of two factors. There's going to have to be two factors because that's what we need to get a quadratic. All right? We're going to need 3 parameters, okay, because there are going to be 3 coefficients to match. Right? Matching 3 coefficients gives you 3 equations and you can solve for the 3 unknowns. All right, but it's just a reparameterization of this, okay? And if you do the matching of the coefficients, you find that these new parameters have to satisfy these relationships to the original controller parameters, k and tau. All right? So, in order for, this to have zeros in the left half plane, that simply corresponds to the real part of lambda 1 and the real part of lambda 2 being negative. Right? And by, that requires this product to be positive, okay? And this Okay, so if lambda 1 and lambda 2 will either be two real values or they'll be a complex conjugate pair. All right? And so what's written down here are just conditions on ensuring that if it's a complex conjugate pair, then this will just be the real part of the complex conjugate pair, because I've got a complex number alpha plus j omega, and I add to that its complex conjugate. What do I get? I just get twice the real part. Okay? And I want that to be negative. All right? So if I want that to be negative, I want minus 1 times that to be positive. Okay? Anyway, so these are just conditions to make sure that lambda 1 and lambda 2 have negative real part. Okay? There's no real tricks there, but it boils down to this has to be positive, right? And this has to be positive. And those two conditions then constrain k and tau. For this, tau's a positive number, right? You know, to get this to be positive, we need this to be negative, so that when we multiply it by minus 1, we get a positive number. And that'll be the case as long as k is less than minus 3. All right? And then you need this to be positive, which means tau has to be less than a third. Okay, so as long as we choose the controller parameters in that way, we'll end up with a stable closed loop. And that analysis has, you know, that result has followed by just analysing the zeros of the denominator of the transfer function. Right? They are the poles. Right? It's the characteristics of the poles that determine whether the transfer function is stable or unstable. For it to be stable, all of the poles have to be strictly in the left half plane. Okay? The rest of the stuff here is just about applying the final value theorem, right? So we know because it's stable, if I put a step in, there'll be some transient response, and eventually we'll just get a constant value out. And the final value theorem can be applied to tell you what that constant value is. And that's all that's happening here, okay, to arrive at an expression for the steady state value of the error signal. So we're applying the final value theorem to the error signal. But of course, the error signal is just a function of, it's the difference between these two signals, so you can express it as a function of what you're putting in and 1 minus the transfer function t. Okay? And the last bit here is just about saying what the frequency response is. Okay? And we've run out of time, so we'll leave it there for today. And we'll start part 3 of the notes next week. It's a disturbance, right? Well, it's not noise necessarily, but if you think, so the input to the plant is the voltage, right? So it's something that's disturbing the voltage somehow. Now, if I push the top, then that will cause some motion that will change the back EMF, right? Which is like a disturbance on the voltage. So it's modelling that. It can represent me pushing it by virtue of the internal feedback that converts motion here or rate of change of position here into a change in the back EMF, and that's like having a disturbance on the voltage, right? But it's not direct, right? Because the input is voltage, it's not torque. If I redid it and said the input is the torque applying to the pendulum, then the force I apply at the top is like a disturbance to the force that's being applied at the bottom. But because it's voltage here, it has to be indirectly through the back EMF. Does that make sense? Yeah. But rather than confuse you with all the details, I'll just leave it out. Right? Make sense? Yeah. Okay.
With that problem set, you're representing tracking.
Yeah, reference to output.
Reference to that. Yep. So how would we sort of understand SI.
S was the
It's related to the disturbance, right?
S was the transfer function from here to here.
Yeah, okay.
So let's say